Hey guys, this video is on electronic structure. That is, where is an electron in an atom? That's what we're going to try to figure out in this video. So we're going to start out talking about Schrodinger's equation. First thing, guys, is you will never have to solve this equation, and at this level, you probably won't even see it again. But this is where pretty much everything we're about to talk about comes from. It all comes out of this equation. So I just want you guys to know, where all this stuff's coming from. So this is Schrodinger's equation, H psi equals E psi. Real quick, there's a lot in here. These are symbols for other things. Psi is something called a wave function, and it's just a mathematical function. Has trigonometric functions in it, like sines, cosines, like that. Exponents, stuff like that. This H with the caret over it is called a Hamiltonian operator, and it has things like partial derivatives in it and stuff like that. E is the energy of the electron. Now we get to something that's useful to us at this level. Psi squared. If we can figure out what psi is, it ends up psi squared, the wave function squared, gives us a handle on the probability of finding the electron in a given volume. Now you'll see in just a minute that we cannot say exactly where an electron is. It's impossible. But what we can do is say it's within this given volume in the atom with some probability. So let's go to the next one. Now, why can't we tell where an electron is? Well, right about the same time that Schrodinger came up with his equation, Werner Heisenberg developed his uncertainty principle. Also called Heisenberg's uncertainty principle. And what he said was this: delta x, delta mv is greater than or equal to h over 4 pi. What does that mean? Well, delta x is the uncertainty in the position of something, whatever we're talking about, probably electrons. Delta mv is the uncertainty in the momentum. Now, m is the mass of whatever we're talking about, v is its speed. Stuff we're talking about, the mass is going to be constant, so it's really the uncertainty in the speed or velocity of what we're talking about. And h is Planck's constant. We've seen this before. It's 6.626 times 10 to the negative 34th joule seconds. Now what this equation says, guys, is that what it says is we can never know absolutely for sure where something is or how fast it's moving. Because the product of so the uncertainty in the position would be, we know where this thing is plus or minus something. So let's say, to make it huge, let's say we know where that football is to plus or minus 1 foot, somewhere in there. That means the uncertainty is 2 feet, minus 1 foot that way, plus 1 foot the other way. And we could calculate, I guess, the uncertainty in the speed like that. Now, we can't actually calculate the actual uncertainty. What we can calculate is the minimum uncertainty, because this equation is an inequality. It says the product of the uncertainty in the position times the uncertainty, basically the speed, has to be bigger than or equal to this number right here. Now, Planck's constant's small. It's really small, but it's not 0. And what that tells us is that we can never know with absolute certainty, with a 0 uncertainty, where something is or how fast it's moving. And we're going to see that in this example right here. So what we're going to do here is calculate the minimum uncertainty in the speed of an electron if its position is known to plus or minus 2 angstroms, roughly the size of an atom. Okay. So all we do is use Heisenberg's uncertainty principle. Here we're looking for the uncertainty in the speed. One of your examples or problems in the worksheets has you calculate the uncertainty in the position, which is probably something more useful. But what we're going to do is use this equation. We want the delta V, the uncertainty in the speed. I've noticed I pulled the m out front of the delta because it's constant for us. So because we want the minimum uncertainty, we use the equality, make this an equals. Okay, so what the uncertainty principle says is that the uncertainty in the speed has to be bigger than or equal to this. The smallest it can be is what we're going to calculate. And so all we do is plug in Planck's constant, 4 pi. The mass of an electron is 9.109 times 10 to the minus 31st kilograms. Notice the uncertainty in the position. Okay, we're told we knew it within plus or minus 2 angstroms. And oh, remember, an angstrom is 1 times 10 to the minus 10th meters. That's one of the conversions I gave you way back in the beginning. So we have 2 times 10 to the minus 10th meters, or 4.00 times 10 to the minus 10th meters as our delta x. All we do now is we plug in Planck's constant, 4 pi, mass of the electron, uncertainty in the position. And look at this. The uncertainty in the speed is 145,000 meters per second, right? So that's basically saying we have absolutely no idea how fast that electron's going. And you'll see when you do the problem in the worksheet that we also would have very almost no idea where the electron is if we know, its speed to plus or minus something, which means, okay, that this is the importance of all this. We cannot know where an electron is, and so it does, and that means that Bohr's model, that of an electron orbiting the nucleus, doesn't make sense, because if it were like a planet orbits the sun, that was what he was thinking, I think, is that if it was, we could know where it is. We could calculate or measure its position. The Heisenberg's uncertainty principle tells us that there's, no matter how good of an instrument we have, it's not a matter of technology, guys. It's a matter of a fundamental property of the universe, is we can never know exactly where something is or how fast it's going. But what we can do, and this is why it was important that we know about psi squared, is we can give a probability that an electron is in a certain volume. Okay? And sometimes we call this the electron density. Now, an orbital, or an atomic orbital, okay, here's a definition. This is an important definition, you guys. An atomic orbital, or any orbital, is a volume of space with a given probability of finding an electron in an atom. And that orbital is given by psi squared, the wave function from Schrodinger's equation. You're never going to have to calculate that, okay? But I'm going to show you. But this is where all the stuff we're about to talk about, this is where it all comes from, okay? So an orbital as opposed to an orbit. Remember in Bohr's model, he had orbits, right? So paths that the electron was supposedly traveling around. And that doesn't work. Heisenberg tells us that doesn't work. And so Schrodinger gave us his equation. And now what we can do is we can say, okay, we can't know where that electron is, but we can calculate that it's in this volume around the nucleus with, say, a 95% probability. And that's the best we can do. We'll take it. This picture right here is the electron density distribution about a hydrogen nucleus. And when you're going to see a couple of these pictures today, or in this video, and in these pictures, the darker the region, the more dense the electron density is, or higher the electron density, which means the higher the probability of finding an electron. And it kind of looks like a sphere, and then another sphere, and then another sphere like that. We'll come back to that in just a few minutes. Now, okay, so that's sort of where all this stuff is coming from, and why we had to go through all this trouble. Now, we start with the stuff that's going to be applicable to you guys. You guys are going to use this stuff. It ends up that in order to describe an electron in an atom, we need to know 4 things. These things are sort of like coordinates describing where something is. NL, okay, we're going to talk about each of these individually. NL, M sub L, M sub S. These are what we call quantum numbers, and they describe an electron in an atom. For a given atom, if we know what all 4 quantum numbers are for an electron, we know everything about that electron in that atom. You can think about, this is an analogy, and no analogies are perfect, but you can think sort of and these kind of go down in level of detail. N, which is the sort of the highest one, might be like what city somebody's in. L might be what street they're on. M sub L might be their house number, okay, what their address on that street. And M sub S might be whether or not they're asleep or awake or something. It ends up, it only has 2 values. It's binary. But that's just an analogy, but the idea is that these describe where an electron is in an atom. Just like if we knew the city, the street, and the number, we would know where somebody was. And then the m sub s, we'll talk about that in a minute. All right, so let's start out with n, the first quantum number, called the principal quantum number. And basically what this tells us is which energy level the electron is in. That is, basically it gives us the rough energy of the electron in an atom. And because when we're talking about electrons with their negative charges and protons in the nucleus with their positive charges, just like in Bohr's model, the farther that electron is from the nucleus, the higher its energy, right? So the higher n is, the higher the energy of the electron, and the farther from the nucleus it is. Higher n means farther from the nucleus, higher energy. Now, here's the rule for what values n can have. N can only be positive integers starting with 1. It can be 1, 2, 3, anything up to infinity. Now, I know it doesn't make sense yet, guys, but just kind of remember the rules, and it's all going to come together here in a few minutes. The next quantum number. So n was like the city, this is like the street. Okay, so this is L. L is the next quantum number. It's called the angular momentum quantum number, and it tells us which sublevel the electron is in. So we have levels that, n equals 1, 2, 3, and so on. And within each level, within each energy level, within each n, there's one or more sublevels, like a subdivision. And within each sublevel, there's one or more orbitals. Remember, an orbital is a region of space within which there's a given probability of finding an electron. And now these orbitals have specific shapes, and the value that L takes tells us what shape that orbital is in, what shape the region of space is that there's a high probability of finding that electron. Now we have, these are old, but we still use them, nicknames for the orbitals. If L is equal to 0, let me back up 1 minute. In white here, this is the rule for what values L can have. That's really important. That's one of the main things you guys want to get out of this slide here, what values L can have. And it depends upon what value n has. So we have to know what city we're in. So we know n. Now we have to know what street we're on in that city. So if n is, so L can be 0, any integer starting with 0, up through 1 less than whatever n is. So if n is 2, the highest value that L can have is 1. It could be 0 and it can be 1, and so on. So now we have these names, these nicknames for these sublevels. When L is equal to 0, that's called an S sublevel. When L is equal to 1, that's called a P sublevel. L equals 2 is called a D sublevel. L equals 3 is called an F sublevel. And we're not going to need these in here because these are theoretical. Well, they're real, but we don't have any atoms that have electrons in them at this point. But when L is equal to 4, that's called a G sublevel. And that's further than we need to go. We're not going to use anything past F sublevel. So remember, L equals 0, 1, 2, and 3. They're just nicknames. They mean the same thing. All right, so we have N, the principal energy level, L, sublevel. Now, M sub L, the magnetic quantum number, tells us the orientation of an orbital in that sublevel. So remember, each sublevel has orbitals, and these orbitals have shapes. That means they have orientations. And what we do is we impose usually it's a Cartesian coordinate system on them, X, Y, and Z axes. We're not going to actually have to go to that level. But that's what's happening here. Now, here's the rule in white for what M sub L can be. And again, just like the values that L can have depend upon what value N has, the values that M sub L can have depend upon what value L has. And the rule for M sub L, it's negative at whatever value L is, negative L, all integers up to up through 0 to positive L. So let's say L is 3. M sub L could be negative 3, negative 2, negative 1, 0, 1, 2, and 3. These are L's, not 1s. Now, the important thing about M sub L for us, guys, is that the number of values that M sub L can have tells us how many orbitals there are in that sublevel. So, and we're going to go through all the permutations here in just one moment, right now. So, I've rewritten the rules for what values these three quantum numbers can have for you up here at the top. Don't worry about m sub s from right now. We'll get to that in a minute. So remember, n, the principal energy level, the values can be any positive integer starting with 1. L can be any integer starting with 0 up to 1 less than n. And m sub L can be negative L through positive L. So let's go through these, at least these permutations down here. So what this is showing is the values for L, the values for n right here. So starting out with the first value that n can have, closest to the nucleus, lowest energy. When n is equal to 1, that means L can be n minus 1, which is it can only have one value, 0. That means there's only one sublevel at n equals 1. And because m sub L can only be negative L through positive L, m sub L can only be 0. Because m sub L only has one value, there's only one orbital in the n equals 1 level, and L equals 0 or S sublevel. So this is, oh, by the way, you'll see levels called shells too. Same thing. A subshell is a sublevel. Same thing. So this is an S sublevel here. N equals 1. Only one orbital. So each box here represents a different orbital. Now, when n is equal to 2, that means that L can be 0 and 1. When L is equal to 0, that means that m sub L is 0. There's only one orbital. N equals 2. L equals 0. One orbital in the S sublevel. But when n is equal to 2, L can also be 1. That's 1 less than n. And so L equals 1 is called a P sublevel. And when L is equal to 1, m sub L can be negative 1, 0, positive 1. It has 3 values, so there are 3 different orbitals in the P sublevel. These are called, by the way, the orbitals take the same name as the sublevel. So the orbitals in the S sublevel are called S orbitals. The orbitals in the P sublevel are called P orbitals. Now when we get to n equals 3, now L can have one more value. It could be 0, so there's an S sublevel with one orbital. It can be 1, so there's a P sublevel with 3 orbitals. And it can also be 2, because 2 is 1 less than 3. And when L is equal to 2, m sub L can be negative 2, negative 1, 0, 1, and 2. It has 5 values, so there are 5 orbitals in the D sublevel. L equals 2 is the D sublevel. And then when n equals 4, we tack on the F sublevel with 7 orbitals in it. So what we're describing here, guys, is where electrons can be in atoms. And so let's go from there. Now we talk about the spin quantum number m sub s. Now the distinction here, guys, is the first 3 quantum numbers we talked about, n, L, and m sub L, describe an address. They describe where the electron can be. You know, city, street, house number. The spin quantum number talks about the actual electron itself. It talks, you know, I mean, the analogy is the person either sleeping or awake. It's only when we get to quantum mechanics, things get really weird. So you're going to see in a minute that with that analogy, if there are 2 people in the same room, that's the most it can be in any house. 2 people can be in one house. One has to be asleep. If one's asleep, the other has to be awake, and vice versa. But the analogy's breaking down. So anyway, m sub s, spin quantum number, describes the electrons, and what it talks about, it's called the spin quantum number because it ends up that electrons act as if they are this spinning spherical charge. They're not. Okay, so that's not a physical description of an electron, but they act this way. What does that mean? It ends up, if you have something that's electrically charged and is spinning, that it creates a magnetic field perpendicular to that spin. And depending upon which way that charged particle is spinning, the magnetic field points one way or the other. So if it's spinning this way, the magnetic field might point north this way, south this way, and if it's spinning the other way, it might be the opposite. Now electrons they act just like this. The distinction though is they are not really this spinning sphere of electric charge. They just act as if they were. They have the same properties. What does that mean? Well, it means when we put them into a magnetic field, they line up with the magnetic field. And there are some experiments that demonstrated this. So the m sub s can only have two values, plus 1/2, minus 1/2. So let me just make sure. That's what I'm saying here. So it has to be either plus 1/2 or minus 1/2. It ends up, we don't care which one at this level. So now back to psi squared. If we make a graph, and you guys are not going to have to do this. This is, again, I'm back to the point where I'm showing you where all this stuff comes from. A graph of the wave function squared, psi squared versus r, which is the distance from the nucleus, gives us what's called a probability distribution. It's the probability that an electron is at some distance from the nucleus. Now, within that given volume, I'm going to define this a little better in a minute. But, okay, so I'll leave it like that. And this is what that probability distribution would look like graphed as a density, where the darker the color, the higher the probability. Right? So it gets slighter as we go out from the nucleus, which would be in the very center right here. So the total probability, this is now we're getting to stuff that's really useful, of finding an electron in a given volume, okay, which is the best we can do around the nucleus, is called the radial probability. And basically, we multiply by some factors right here. We're not going to do it, so it doesn't matter. But the graph looks like this right now. And if we rotate this graph in 3 dimensions around the x-axis, y-axis, and the z-axis, what we get, well, this graph gives us basically a sphere. And that's the shape of the orbital that's described by this wave function that we used for this right here. This isn't the actual wave function, this is just a factor. But there's a couple things about this. It does go to 0 at the nucleus, and that's a good thing because we shouldn't be able to find the nucleus occupying the same volume as an electron. And right down here, this tail, the probability asymptotically approaches 0 as r goes to infinity. That has some pretty strange results or meaning. What that says, and this is a real thing, this says that electron has some probability of existing at any distance up to infinity away from its nucleus. So every single atom in the universe, okay, has some probability of existing anywhere in the whole universe. So as we speak right here, as I speak right here, the atoms that are in my arm have some probability of wherever you're at of being the same place. And that's pretty extreme. And the actual probability, it gets extremely close to 0 very rapidly, but it's not 0 until you get to infinity. Anyway, that's just mind-blowing to me. So now, again, this is all sort of where everything's coming from. You're not going to have to actually do this stuff right here, but I want you to see it. This is the probability density up here, the top 3 graphs, and this is a probability per given volume. And that's why this blows up at r equals 0, because you're basically dividing by the volume. As the volume goes to 0, this goes to infinity right here. A much more useful thing for us, and this is really what we think about, is the what's called the radial probability distribution. Again, I'm not going to ask you if you know the difference between the two. I'm giving you background. What this is, at a given radius, is the probability per distance that the event, that means that the electron exists in this thin spherical shell. And what happens, okay, so if we look at these graphs down here, these are useful graphs to know. I'm gonna ask you guys to think back on this in the next video and remember this. Okay, so if we look at, this is the n equals 1, L equals 0 wave function. So this is a 1s, what we call that, a 1s orbital. And so if we rotate this graph about all 3 axes, we get the shape of that orbital, which is a sphere. And this would be a slice out of it. Now, when we go to n equals 2, we're at the next level out. This can be the same exact atom. We're just one level out. At n equals 2, L equals 0. This is also an s orbital in an s sublevel. It's what we call a 2s orbital, where the 2 in front of the s is the n. Now, a couple things about this. Again, if we rotate this about all three axes, we get the shape of the orbital. And from the outside, it looks like a sphere. But if we can reach inside that sphere, see where this graph touches the axis? That actually goes to 0. That's what we call a node. And inside that orbital, there's a region of space where this goes to 0. And remember, what this is graphing. It's the probability of finding an electron there. And so there's this region inside of this orbital where there's 0 probability of finding that electron. It can be out here, and it can also be in here too. Notice it reaches it past that node until we get to the nucleus. Now when n equals 3, okay, at the s sublevel, notice that there's another node, right? So we have the highest probability is out here. Then we have a 0 probability, a node, then a smaller probability, then a node, then an even smaller probability. But it's not 0, it reaches right in here. So this gives us the shape of s orbitals, which is the single orbital at any s sublevel at n equals 1, 2, 3, 17, what have you. There's an s sublevel with one orbital called an s orbital, and they are spheres. Okay? But anything past n equals 1, that s orbital has nodes within it, and then other regions of non-zero probability. Okay, so that gives us the shape of an s orbital, a sphere. When L equals 1, now I'm not going to go through all that for anything else, okay? But when L equals 1, which is the first time we see this, is when n is equal to 2, then we have what's called a p sublevel or p subshell, and there are 3 orbitals in that p sublevel, and they look kind of like this, and they're oriented along different axes, the x, the y, and the z maybe. So sometimes you'll see them called the px, the py, and the pz. We don't really care about that distinction at this level yet. When L is equal to 2, we have a d sublevel, and in every d sublevel or d subshell, there are 5 d orbitals. The first time we see this is when n is equal to 3. And the names are, again, these describe these shapes: dx squared minus y squared, dz squared, dxy, dxz, and dyz. I'm not going to ask you to know those. You should recognize roughly these shapes, but I'm not going to ask you to draw them or anything like that. I sure can't draw them. But those are d orbitals at the d sublevel, which first appears when n is equal to 3. L equals 2. All right, so now we're almost to the point, guys, where we can start putting electrons into these orbitals. So we're describing the house on the street in the city, and now we have to start putting some people in those houses. So the first thing is all the orbitals in a given shell or level have the same energy if there's only one electron in the atom. Now that's not very interesting, and that's not most of the time there's more than one electron, but we need to start here. So when if there's only now, it's really important you remember this is only if there's only one electron, no other electrons. The 1s orbital in the 1s sublevel has a certain energy. It's the lowest. By the way, I've kind of snuck this notation in on you. The 1s, 2s, 2p, what you're seeing here, the number in front of the letter tells you n. So n equals 1, s sublevel. N equals 2, sublevel. N equals 2, p sublevel. 3 orbitals in the p sublevel, and so on. All the orbitals at the n equals 2 level have the same energy if there's only one electron, at 3 and at 4 and so on. And that's not very interesting. So let's start putting more than one electron in. Now, once you do that, what happens is the different sublevels, their energy splits. And so at any given energy level, or n, that s sublevel is lower in energy than its p sublevel, which is lower than its d, which is lower than its f sublevel. But we get some mixing in here too. So this, guys, this is a very important diagram. It will be really helpful for you guys to kind of have this picture in your mind. Again, what this is describing is the energy of electrons in orbitals, in sublevels, in levels, in an atom. So the 1s sublevel is the lowest energy that an electron can be. The next energy level, or next energy higher up that an electron can be in, is 2s. Now, Remember, in nature, low energy is good. So electrons, we're going to see in a minute, all want to have the lowest energy they can have. So they're trying to get into the lowest energy orbital that they can. 2s is the next, and then 2p, these three of these 2p orbitals are the next highest energy. And then we get to that. That's everything that's at the n equals 2 level. At the n equals 3 level, there's the 3s, the 3p, and the 3d. 3s is lower in energy than 3p, which is lower than 3d. But look at this. See that 4s right there? It ends up that we get this mixing here, and it ends up that it's lower in energy just a little bit for an electron to be in a 4s orbital than it is to be in a 3d orbital most of the time. And so what happens is, most of the time, the electron goes here instead of here, if it can. And then after we go past the 3D, then we're still in the 4 level, 4p. And also, 5s does the same thing that 4s does. It sneaks underneath the 4d orbitals. And then 6s sneaks beneath the 5ds, and so on. It ends up that when we get to the f's, they slip 2 down, actually. So when we get to the 6s, then the 4f's come next, and then from there. But we'll get to that in a minute. So these are the relative energies of orbitals or electrons in an atom, in orbitals, when there's more than one electron. So where we're going with this, guys, is figuring out where to put these electrons in these orbitals, in these sublevels, in these levels, in these atoms. We have rules that tell us where the electrons can exist in the orbitals. And the rules come from, well, I mean, it's nature, but they're within Schrodinger's equation. They fall out of that. It's really, really cool. Anyway, so the Aufbau principle. All this says is that electrons, okay, if they can, will always go into the lowest energy orbital that's available. And we're going to talk about what it means to be available in just a minute. But remember that picture we're just looking at, right? 1s is lowest energy, then 2s, then 2p, and so on that. So when electrons exist in atoms, they're going to go into the lowest energy orbital that they can fit into. So if the 1s orbital has room, that's where the electron's going to go. And if it doesn't have room there, then it's going to go into the 2s. And if that doesn't have room, then it's going to go into a 2p, and so on. And so in these kind of diagrams that I'm showing here now, okay, this is energy going up. This is really similar to what we were just looking at. Each line now represents an orbital. This is 1s, it's lower in energy than the 2s, and these arrows, guys, represent electrons. And so if we had another electron we wanted to put in here, it ends up we can fit 2, and I'll tell you that in a minute. But the next electron would go here, and then it ends up that would be full, and after that the next electron would have to go here. That's the Aufbau principle. It just says electrons go into the lowest energy available orbital. Next, Hund's rule. When we have, okay, so if you remember, right, those the 2p, 3p, the 3d, and it ends up the f's, they all are the same at the same energy. So all those 2p orbitals at the 2p sublevel were all at the same energy. They're what we call degenerate, the same energy. So when electrons go into degenerate orbitals, they always go one electron into each orbital first before we put another electron into there. And now these arrows that we use to describe electrons, we use arrows because remember m sub s says that they're either spin up or spin down, plus or minus 1/2. Spin down might be minus 1/2 and spin up might be plus 1/2. It doesn't matter which. So now if we're going to put another electron into this 2p sublevel, it's going to have to go into either this one or this one. And whatever the spin of this first electron is, down or up, doesn't matter. Whatever it is, the next one has to have that same spin there. And then if we were going to put another electron in, then it would go right here with the same spin. That's Hund's rule. And that applies when we have degenerate orbitals. So at the same sublevel, p orbitals are degenerate with each other, d orbitals are degenerate with each other, and then f orbitals are degenerate with each other. That's Hund's rule. Next, the Pauli exclusion principle. So what Wolfgang Pauli, really what he says is that for any atom, no two electrons in that atom can have all four quantum numbers identical to each other. So at least one of those quantum numbers has to be different for those two electrons. Now, as a practical matter, what that means for us is that if we've already determined N, L, and M sub L, so we know what house on what street and what city that electron is in, then the only thing that's left that can differ is M sub S. And so once we pick an orbital, so by choosing a specific value for N, L, and M sub L, we've picked one orbital in that atom. And so now when we put electrons in that orbital, for them to have some quantum number different, M sub S has to be different, spin up or spin down. So as a practical matter, it says this: no more than two electrons can exist in the same orbital, and if they are in the same orbital, they have to have opposite spins. So let's say we have 2, 4, 6, 7, 5, 6, 7 electrons here. Remember, Hund's rule says that these electrons had to go one into each, all at the same spin. Now the next electron that goes in doesn't matter which one, goes into one of these three, but it has to have the opposite spin. If these are spin down, this has to be spin up. If these were spin up, this would have to be spin down. Once we do that, there's no more room in that orbital for any more electrons. Okay, so this one's full, has 2 electrons, opposite spins. 2s is full, 2 electrons with opposite spins. And then one of these 2p's is full. There is room for 2 more electrons in each of these 2p orbitals. Okay. So now applying those rules gives us what we call electron configurations. And so now again, at this point, guys, we are talking only about neutral atoms that have a total of 0 electric charge. And what that means is they have the same number of electrons as they do protons. And so we can look at a periodic table and we can tell how many protons an atom has just by reading its atomic number. Hydrogen is 1, has 1 proton, 1 electron. It goes into the lowest energy orbital that has room, which is the 1s, and it's either spin up or spin down, doesn't matter. The electron configuration for a neutral hydrogen atom in what is called its ground state would be 1, that's the N, S, that's a sublevel and the name of the orbital. And this superscript says how many electrons are in that sublevel. So 1s, 1. That's how we say that. Lithium has 3 protons, 3 electrons. So, oh, by the way, in this sort of diagram, guys, it's just like that one that I showed you a minute ago where the 1s is lower than the 2s and then 2p. It's just the energy goes to the right instead of up here. So 2s is higher in energy than the 1s. Lithium has 3 electrons. 2 of them went into the 1s, then it's full, the third one went into the 2s. The electron configuration would be 1s2, so n equals 1, s sublevel, 2 electrons, 2s1. Boron, which has 5 protons and 5 electrons, would be 1s2, so we always start with 1s and then 2s, 2. Now we have an electron in the 2p sublevel. It doesn't matter which of these orbitals it's in, which spin it has, up or down. But its electron configuration would be 1s2, that's these 2, 2s2, and 2p1. Nitrogen has 7 electrons, 1s2, 2s2, and each of these 3 2p electrons went into a different 2p orbital, the degenerate orbitals. So its electron configuration would be 1s2, 2s2, 2p3. Now, if you're reading around, you may find something that says 2px1, 2py1, 2pz1. We don't really care about that distinction at this point. Now, that can get pretty complicated trying to draw these what are called energy level diagrams to figure out an electron configuration. So, okay, this is important, guys. Electron configurations are part of the language that we speak in chemistry. We use these as words. And we can read the electron configuration for any element by looking at the periodic table. And that's what I'm going to show you guys how to do right now. So there's a periodic table. A couple of things. Remember these first 2 columns, the alkali metals, are called the S block. And that's because the last electron to go into each of these elements is an s electron, goes into an s sublevel. Matter of fact, everything that's in the first column only has one electron in that last s sublevel, so it's going to end in S1, its electron configuration. Everything in the second column has two electrons in that s sublevel, so it's going to end in S2. This is the p block over here, starting right here on over. And so, except for helium, helium is kind of weird. There's only two electrons, but other than helium, the last electrons to go into each of these elements goes into a p sublevel, and boron ends in P1, carbon ends in P2, and nitrogen P3, P4, P5, and P6. So that means there's one electron in the p sublevel for everything in this column, in the last p level, two electrons in the last p sublevel for this column, 3, 4, 5, and 6, starting with neon. This is the D block, okay? And so the last electron that goes into each of these atoms goes into a D sublevel. And with some exceptions I'm going to show you in a few minutes. It's D1 here, D2, D3, D4, D5, D6, D7, D8, D9, D10. And the F block is down here. Now the F block comes in, you see this asterisk right here? It comes after this asterisk right here. Now, you see a couple different ways of showing the F block. It's always down beneath the rest of it. The only reason that we write it beneath everything else is it would be very awkward to typeset something like this, because we'd have this really, really thin strip in the middle, and then everything else would be just so it's too small to see. It'd be awkward. So we put it down here. But really, it goes right here and here. Sometimes you see lanthanum down here and actinium down here, but the reason I have lanthanum and actinium down here is for reasons beyond the scope of this class. These are characterized as D block elements, and these are F block elements. That's the way it is. And so the last electron to go into these atoms is an F electron, F1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, real quick, before I get to the rows, notice something. If you remember, at every s sublevel, there's only one s orbital, a single s orbital. And we know that every orbital can hold two electrons. Well, look at this. There's two columns in the s block. And at the p sublevel, there are three orbitals. Two electrons each is 6 electrons, 6 columns. In the d sublevel, there are 5 orbitals. Two electrons in each is a total of 10 electrons, 10 columns. At the f sublevel, 7 orbitals, 14 electrons, 14 columns. Okay. Now next, reading electrons, configurations. For the s block and the p block, the row number is n. Okay, so what we're doing here is we're reading the last electron that goes into that atom. N equals 1, 2, 3, 4, and 5. When we get to the D block, the N is 1 less than the row number. So we're talking about 3D orbitals here, because this is 5, 4D orbitals here, 6, 5D orbitals here, and 7D orbitals, 6D orbitals here, 5D and 6D. And for the F block, it's N minus 2. So remember, cerium 58 goes right here. So this is 6, these are 4F electrons, and then row 7, these are 5F electrons. All right, so now we can start reading electron configurations of any element directly from the periodic table. Let's start with hydrogen. Only one electron, so it's 1, that's the row number, so that's the N. S, it's in the S block, and a first column, so 1s1, easy. Helium, based on electron configurations, it would go here, it'd be 1s2, but it's here for because of the way it behaves. It behaves like the noble gases. And then let's get down to lithium. So when we're saying or writing the electron configuration, guys, for any element, we always read through the last element in every block up before that, and then through that element. So lithium, the last element in the S block would be helium, so it would be 1, we say 1s2, and then come down here to 2s1. Okay, that's the lithium's electron configuration. Beryllium will be 1s2, 2s2, and so on. Boron, we would say 1s2, that's the last element in that block, 2s2, that's the last element in this block, and then 2p1, we're at boron, and so on. So let's go. So you can see as we go down in the periodic table, get more and more electrons, and this gets more and more not convoluted but involved. So let's say we're doing titanium. Here's how we'd read it. So remember, we have to go through every element in the last block. By the way, when we read the periodic table, it's just like reading a book, left to right, top to bottom. So going through each row, top to bottom, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d12. That's a lot, right? But it follows the pattern, and so we can do everything just like that. So you'll definitely get some practice doing that. However, because that gets really long and there's all these numbers and letters, and it's really, really easy to get things mixed up. For example, francium down here, this is how you would write its electron configuration, what's called the complete electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so on, all the way up through 7s1. See, it's 7s1 right here. But we have core notation, also called noble gas notation. And what you do is you just put whatever element you're writing the electron configuration of, you write the previous noble gas. Remember, we read the periodic table left to right, top to bottom. So the previous noble gas, as we go left to right, top to bottom before francium, would be radon. So we just put the symbol for that element in brackets. And what that does is that stands for all the electrons up through radon. So these electrons here, that's radon's electron configuration. That in the brackets, that stands for all those electrons. And then we just have to read the element we're talking about. So radon and then 7s1. Easy, right? So helium, lithium, we don't, no real need to do this, but it would be helium 2s1, just like that. So that's core notation, really handy. Now there are some exceptions. These are, by the way, these are not the only exceptions in the periodic table, but these are the only ones I'm asking you to memorize. So if we just went through the way that I showed you just now, and we were to write down, just following the rules, the electron configuration for chromium, Cr over here, we would get argon 4s2, 3d4, because we fill the s block and then we go to the 3d. But it ends up, it's an exception. Its actual configuration is argon 4s1, 3d5. Likewise, copper is not argon 4s2, 3d9, but it's argon 4s1, 3d10. Same thing with molybdenum. It's krypton 5s1, 4d5. Silver is krypton 5s1, 4d10. And gold is xenon 6s1, 4f14, because we're in the F block, and then 5d10, not 6s2, 4f14, 5d9. So these are exceptions. There's a pattern, right? So if you look at the periodic table, chromium is right above copper, right? So the only thing that's different here is, different noble gas, because it's a different row, and this is 4, this is 5, this is 3, this is 4. Same thing, copper, silver, and gold are all in the same column. They're all 4s, so all S1, D10 something, and with a 4F thrown in here. Well, that's all there is to that, guys.